Good morning, students. We are starting once again with electrochemistry. As discussed in the last lecture, we studied the construction, working and the principle of a Daniell cell, that is an electrochemical cell. In that we had seen that it basically consists of two half cells, one which is anodic half cell and the other which is cathodic half cell. And in the last portion of that we saw what is electrode potential. So we are going to discuss today in detail about electrode potential and its measurement. What is electrode potential? Electrode potential occurs due to separation of charges. Now, why do the separation of charges occur in an electrochemical cell? Let us look into it. Now, if you remember, this is the construction of an electrochemical cell. Here, a zinc electrode is dipped in a ZnSO4 solution and copper electrode is dipped in a copper SO4 solution. Now, as discussed here, zinc electrode undergoes oxidation and there is accumulation of Zn2 plus ion within the solution, and the electrons that are released will get accumulated on the electrode, making this electrode negatively charged, and hence the symbol that is given to anode is minus, and we say that the anode in an electrochemical cell is negatively charged. And due to this accumulation of electrons on the metal rod and the accumulation of positive ions in the solution, a potential difference develops between the metal and the electrolyte junction, and this potential difference is termed as oxidation potential. Similarly, in the beaker B of an electrochemical cell, we have seen that reduction occurs. The metal ions from the solution will accept the electrons and the metal will get deposited on the electrode, increasing the weight of the electrode, and here again, once again, there is separation of charges, that is, the rod becomes positively charged and the solution becomes negatively charged, and hence again here a potential difference develops between the metal and its solution, and this potential difference that is developed at the cathodic half cell is termed as the reduction potential. Now the question arises, why does the anodic half cell undergo oxidation? Why does the cathodic half cell undergo reduction? Students, this is not given in your textbook, but still we have to discuss it from the point of JEE and NET exams. Okay, we need to discuss why the separation of charges occur. Separation of charges occurs due to two factors. The first is the solution pressure SP and the second is the osmotic pressure OP. Now, what is the solution pressure? Solution pressure is the pressure within the solution that has the tendency to convert metals into metal ions. So basically that has the tendency to dissolve the electrode into the metal ions and the metal ions gets accumulated in the solution. What is osmotic pressure? Osmotic pressure you will be studying in solutions chapter. Osmotic pressure has the tendency in which metal ions will accept the electrons and gets deposited on the electrodes as metals. That is, reduction occurs and the weight of the electrode increases. So, what determines that in a given half cell oxidation occurs or reduction occurs? If in a given half cell solution pressure is greater than the osmotic pressure, then oxidation occurs. Due to this, the weight of the rod decreases, and such a type of potential difference that is developed is termed as oxidation potential. What determines that in a given half cell reduction occurs? When the solution pressure is less than the osmotic pressure, then the metal ions from the solution will accept the electrons and gets deposited as metal on the surface of the cathode. As a result, the weight of the cathode increases and the potential difference that is developed is termed as reduction potential, represented like this. Now, if you remember, in a galvanic cell, If you remember, in a galvanic cell, we have connected both the half cells via a voltmeter, and the reading of the voltmeter will be giving you 1.10 volts if a zinc half cell is the anode and the copper half cell is the cathode. So basically we need to understand what is cell potential. What is cell potential, which is represented by the symbol E cell. So basically we can say the cell potential of a given galvanic cell is the sum, that is the addition of the cell potential of the anode and the cell potential of the cathode. So we can write it in the formula like this, that the cell, E stands for potential, cell potential is equals to oxidation potential at anode, because at anode oxidation occurs, plus the reduction potential at cathode. So whatever is the reading here in the voltmeter is equals to the sum of the oxidation potential of anode and the reduction potential of cathode, and that will give you the overall cell potential. Now IUPAC, if you remember, full form of IUPAC is International Union of Pure and Applied Chemistry. IUPAC found out experimentally that the oxidation potential is equals to the negative value of the reduction potential. So if I say that say zinc half cell has an oxidation potential of 0.76 volts, then the reduction potential of the zinc half cell will be minus of 0.76 volts. Now substituting here, we can say that oxidation potential at anode is equals to the negative value of the oxidation potential of cathode, or simultaneously we can say the reduction potential at cathode is equals to the negative value of the reduction potential of anode, and hence we get the equation to calculate the cell potential. If we substitute this in this equation, we will get the formula to calculate the cell potential. Cell potential is equals to reduction potential at cathode minus reduction potential at anode. Once again I am repeating, students, the cell potential is equals to reduction potential at cathode minus reduction potential at anode. Vice versa, in terms of oxidation potential, we can write that the cell potential is equals to oxidation potential at anode minus oxidation potential at cathode. But IUPAC has decided that worldwide, for the calculation purposes, we will be using the reduction potentials. So whenever in a given sum or in the textbook it is mentioned only the electrode potential, we are talking about the reduction potentials. Now question arises that teacher, when you said that oxidation potential of zinc half cell is 0.74 volts, how did that value come, or how do you measure the electrode potential of a given half cell? Then we are going to discuss how to measure the electrode potential. Electrode potential, standard electrode potential and non-standard electrode potential. Now what do you mean by standard electrode potential? Standard electrode potential is the measurement of electrode potential under standard conditions. We have already discussed this in 11th standard. क्या है standard conditions? Temperature 298 Kelvin, pressure 1 atmosphere, and the concentration of the solution should be 1 molar. As opposed to that, if you consider non-standard conditions, the non-standard conditions will be temperature is not equals to 298 Kelvin, pressure is not equals to 1 atmosphere, concentration is not equals to 1 molar. So how do you measure a standard cell potential? The measurement of standard cell potential is done via a half cell which is termed as a She electrode. The full form of She electrode is standard hydrogen electrode, because we are measuring the cell potential under standard conditions. Now, what is the construction of a She electrode? The construction of a She electrode it is a gaseous electrode in which hydrogen gas is bubbled in via this glass chamber, and in that the gaseous electrode consists of an inert platinum strip which is coated with platinum black, and it is dipped inside a solution of H plus ions whose concentration is 1 molar. Mind you students, here the entire She electrode works under standard conditions, and hence the pressure of hydrogen gas is 1 bar. The concentration of H plus ions that are filled in the solution is also 1 molar. For that you can take any of the acidic solutions. And the most important point, why do we consider the standard hydrogen electrode only for the measurement of cell potential, that is the standard cell potential? Because here the IUPAC has assumed that the oxidation potential or the reduction potential of the standard hydrogen electrode is 0 volts. Now how is this useful to us? Now if you remember the formula of standard conditions represented by this degree sign, standard cell potential. Once again I am repeating, standard cell potential is equals to standard reduction potential at cathode minus standard reduction potential at anode. Now we have already said that here, if you can look in the diagram, in this consists of an electrochemical cell in which the anode half cell is a She electrode and the cathode half cell is a copper half cell. In this, both are connected via a voltmeter. It was observed when this cell functions when hydrogen electrode, standard hydrogen electrode is anode and the copper half cell acts as cathode, the cell potential is equals to 0.34 volts. So this value if we substitute in the given equation, 0.34 volts is equals to standard reduction potential of the copper half cell minus standard reduction potential of She electrode. But as I told you that the standard reduction potential of She electrode is 0 volts. So as a result, substituting here, we will get the equation that the standard potential of the copper half cell, standard reduction potential of the copper half cell will be equals to 0.34 volts. So this is students how you calculate the standard potential of any half cell. So what the IUPAC people did was, She electrode they kept as the anodic half cell, and जिसका भी half cell का electrode का measurement लेना था, they made it as cathode. So if you substitute in this equation, whatever is the reading that you are getting in the voltmeter, because the standard cell potential of the hydrogen electrode is 0, the value of the given half cell, the standard reduction value of the given half cell can be obtained, and on the basis of that they got the values of say standard zinc potential, reduction potential as minus 0.76 volts and the standard reduction potential of copper as 0.34 volts. And as a result, we come to know that substituting in this formula for a given Daniell cell, the standard cell potential of a Daniell cell comes equals to 1.10 volts that we have already taught you in the first lecture. Now, another important short topic is the cell representation. How do you represent a given cell? हर बार थोड़ी तुम लोग लिखोगे कि ये एनोड है, इसमें डिप किया गया है, सॉल्ट ब्रिज कनेक्ट किया है, ये कैथोड है. We need to represent this entire construction in a, you can say, concise manner. So as a result, IUPAC has given this formula for cell representation, wherein on the left hand side you will write the anode portion and on the right hand side you will write the cathode portion, and the vertical lines will represent the separation that occurs between the metal and the metal electrolyte junction. So for this construction we can write, as you can see, the platinum strip is in contact with hydrogen gas, that is bubble, which is dipped in H plus aqueous solution. The double line indicates the salt bridge whose both ends are dipped in both the half cell, and the other end, if you can see, copper ions which are in contact with the copper electrode. If you see here students, always on the left hand side part oxidation occurs, that is metal gets converted into metal ion, and on the right hand side, that is the cathodic part, reduction occurs, that is metal ions get converted into metal. So let me remind you, whenever you write the cell representation, remember lone. This is a shortcut that you can remember. What is the lone part? Left side in an electrochemical cell, oxidation occurs, so you can remember metal to metal ion. It is the anode part, and anode is always negative. So that is how you represent a given cell. So students, using the standard hydrogen electrode, we can measure the standard reduction potentials of the different half cells. Now what the IUPAC did was, they arranged the standard reduction potentials of the various half cells in the decreasing order of the reduction potentials, and they got a series from higher values to the lower values. They got a series, and that series is termed as a EMF series. EMF, you are already familiar with the word, that is electromotive force. So in an EMF series, please refer to your textbooks, page number 71. The values of the reduction potentials of the various metals have been given, for which we will be using further in the sums, which are important for both your state board exams and the NET exams. Let us focus on the textual sums first. Sum number 3.2 of the textbook. The question that is given is, can you store a copper sulfate solution in a zinc pot? Now for this, we need to know the standard reduction potentials of both the copper half cell and the zinc half cell. As you can see here, the standard reduction potential of copper is 0.34 volts, and the standard reduction potential of zinc is minus 0.76 volts. Now the question arises, when can you say that it is safe to store a given solution in a given container? When no oxidation or reduction reaction occurs, that is, there is no exchange of electrons. So basically, whatever is the container material should not undergo oxidation, and whatever is the solution material should not undergo reduction. Now if you can see the standard reduction potential values, so if you can see, according to the standard reduction values, for the reaction to occur, copper half cell should act as cathode and the zinc half shell should act as anode. And if you can look at the values and compare it, it collaborates this thing, that if copper sulfate solution, which has more reduction potential, is stored in a zinc pot, then the reaction will occur and it will be a spontaneous reaction, and so it will not be safe to store a copper sulfate solution in a zinc pot. The another type of sum, students, that the second textual sum that we are focusing on it is, please take out your textbooks to page number 93, sum number 3.1. Read the question. Arrange the following metals in the order in which they will displace each other from the solution of their salts. The given metals are aluminum, copper, iron, magnesium and zinc. Now if you look in the EMF series given on page number 71, standard reduction potential of aluminum is minus 1.66 volts. Standard reduction potential of copper is 0.34 volts. Standard reduction potential of iron minus 0.44 volts. That of magnesium minus 2.36 and that of zinc is minus 0.76 volts. Now student, question arises, when can we say a given metal will displace the other metal from its solution? When its oxidation potential is more than that of the other ones. In short, if you arrange this in the increasing order of the reduction potentials, we can say that the given metal will displace the other metal from its solution. So if you can see the reduction potential values, the least reduction potential value is of magnesium, then that is minus 2.36, then that of aluminium, then zinc, then iron, and the highest reduction potential value is of copper. So those substances which will have a higher reduction potential values will be easily displaced from their solutions, and so the answer will be magnesium will displace aluminium, aluminium will displace zinc, zinc will displace iron, and iron will displace the copper. If you remember, this might be there in your 10th standard syllabus in the term of activity series. Subsequently, there is another sum given on page number 93, the next sum number 3.2. Given are the standard electrode potentials of the following half cells: potassium, silver, mercury, magnesium and chromium. Arrange these metals in the increasing order of the reducing power. What do you mean by reducing power? That is their ability to reduce the other substances. Now when can we say a given substance has a higher reducing power? Because the question asked is increasing order of the reducing power. Those metals which have a lower standard reduction potential. Once again I am repeating, those metals which have a lower standard reduction potential will have a higher reducing power. And since the values are already given in the sum, we can arrange them in the following pattern. That is, the highest reduction potential value is exhibited by silver, which will be having the least reducing power, then mercury, then chromium, then magnesium, and the highest reducing power will be shown by potassium.